But they're not very far apart now because our final got moved, right?
It's like
Thursday is our, then our last test is Monday, or is our last test Friday?
I think it's actually Friday.
Okay, well, that's good.
So we have like 4 days.
That's good because I can give you your tests back on. Well, I could probably scan them so y'all can study them over the weekend if it would be helpful. But I could definitely give them to you Monday. Okay.
All my finals on Wednesday, which is now, and then one final on like the last day, so I'm just kind of there.
That's what they did to me. I have OChem at 8 a.m. and then right after I go here.
Oh.
When before it was like OChem on Saturday, and I was like, that's fine because
Yeah,
I don't
right.
care. I mean, that's just final exam for me. They're like, no, let's not do that on Saturday.
Which is good for y'all. I mean, bad for y'all, good for us. Because, you know, I have to pay a babysitter to come and get my finals, and all my babysitters are here taking finals. So it's kind of a, yeah. Okay. So today we start Unit 4. Oh, I can't zoom. But I hate the way that's laid out. How do I make this be better? Zoom plus.
Zoom is -2%.
Go. That's good. I like it. Zoom 5. Okay. So today we're going to start with talking about relations. This is my very favorite thing these proofs are my favorite proofs to write. So I'm excited to do this today. And then after we do this, equivalence relations are the last proofs we'll write. And then we'll start drawing pictures and doing counting and probability. So, because we're almost done, which is alarming for a lot of reasons. Yes, I have a lot of things to fix. Janaya, I still never moved the homeworks. I responded to your email finally, but I didn't move the homeworks, but I will move them. I don't know what homeworks, what was due on Friday?
It was Thursday.
Thursday. Okay. What sections was it? You just need me to extend stuff. Alrighty. I'll do that.
I'll just look it up.
Okay, so relation is, I mean, this is what we know of as a relation. Like if I asked you in college algebra, what's a relation, then you would tell me like it's a set of ordered pairs, right? And then if we're talking about, you would, yeah. And then a function is a relation where every input has one output. Yeah. So like this is just making that more mathy. So a relation on a set A to B, from A to B, is a subset of A cross B. So it's a set of ordered pairs. That's what A cross B is, where the first thing is in A and the second thing is in B. What makes this different than a function is that it doesn't have to be a function. So every input could have a couple of outputs. Okay, so we say that X is related to Y by R, and we write this, X, R, Y, X is related to Y, if and only if the pair X, Y is in the relation. This is a lot of notation with no context, so let's go ahead and do some context with some examples. But first, talk about what A cross B is. Remember, this is the set of ordered pairs A, B, where A is in A and B is in B. So a function is a relation, right? A function is a special type of relation where every input has one output. So the relation here, R, is going to be equal to the set of ordered pairs A, F of A. That's like how this relation would work. You know, A is in big A. F of A is in B. You could say that A is related to F of A. Any graph in R2 is also a relation. It's not a function necessarily, like think about a circle. So a circle is not a function, but a circle is a relation. Sorry, that was hard to see. So if we were talking about, like, I don't know, think about x squared plus y squared equals 1. So your unit circle. So this, looks like a circle. Radius is 1. Thus, these are the ordered pairs x, y. Those are the ordered pairs in the relation, right? It's not a function, but it is a relation. So the relation here R is going to be the set of all ordered pairs x, y, where x squared plus y squared equals 1. On that next one, A is U.S. cities, B is U.S. states. We can define a relation R equal to A, B, where city A is in state B. How does that feel? I hate the way that this looks. Also, it's freezing in here, right?
Yeah.
Ugh. It doesn't help that I don't have any air conditioning in my office, so I'm used to that. Okay. So this relation R would be that the ordered pairs A, B are in R if city A is in city B. State B, I mean. So R then would be equal to things like Charleston, South Carolina, or Nashville, Tennessee, or Fayetteville, Arkansas. I'm just listing all the cities I've lived in. Birmingham, Alabama. I think that's all. Charleston's the only city I've lived in as a full-blown adult. So it's just different. Like, this was growing up. This was college. This was grad school. So, like, this is the only one that I've had, like, a real job and money. But also children. So, it's just different. It's hard to compare. I love them all. I would move back to any of these cities in a heartbeat. Nashville would be the toughest one because Nashville's insane now. But my family lives there, so I could deal with that to be near my family and my best friend. So, but yeah. Okay. So let's look at this relation T on the real numbers. So T is this relation where xy is in T if x squared plus 3y squared is 4. So this is like a graph basically in R2 in the Cartesian plane. So you're looking at x squared plus 3y squared is 4. This is some sort of ellipse. Hey, I'm teaching ellipses in pre-cal today. So T is this relation. Are there values of x in the real numbers where x1 is an element in T? If so, what are they? How do we figure that out? Yeah, so we're going to plug in 1 for y. So we have, oops, that's not a pin. We have x squared plus 3 times y squared equals 4. That would be x squared plus 3 equals 4. So x squared equals 1. So x is plus or minus 1. So both 1, 1 is in T, and negative 1, 1 is in T. So these are elements in the relation. Elements in the relation look like ordered pairs. Are we okay with that? A relation is a set of ordered pairs. A function is a special type of relation, right? Okay. Are there values of y, also real numbers, where 4y is in t? If so, what are they? Let's try. So if I make 4 my x value, I try to figure out what y values would make this true. This is 16 plus 3y squared is 4. That's 3y squared is negative 12. That seems problematic. So y squared is negative 4, right? Which is square rooting would not be a real number. So no, there are not. Do you have any questions so far? Do you feel okay about what a relation is? We're going to keep going, so if you're a little bit confused, that's okay. Okay. So, properties of relations. So a relation is on some set X. R is reflexive if for every X in X, X is related to X. That means that every element is related to itself. It's reflexive. It looks at itself under this relation. Good? Okay. We'll talk about examples of these in a minute. R is symmetric if for all x, y, and x, if x is related to y, then you can reverse that order. Then y would also be related to x. Notice that both of these are if-then statements. If x is in x, then x is related to x. If x and y are in x and x is related to y, then y is related to x. And then third, we have R is transitive, provided you have x, y, and z. If x is related to y and y is related to z, then you can squish out the middleman and you're just looking at x is related to z. So that first one, every person is related to its own self. The second one for symmetry, relatives are related to each other. And for transitivity, relatives of relatives are relatives. So what we want to figure out, we're going to do this in sets to just make sure that we understand each of these properties. So we're going to do 4 examples of reflexivity, then we'll do 4 symmetry, and then 4 for transitivity. So A is a set of all people. R is the relation that consists of pairs of people, X, Y, where X and Y have the same mother and father. So for all of these questions, we're looking at R, is this reflexive? So if for all X in X, is X related to X? That's what we want to answer. So on this first one, for all people, does X have the same mother and father as X? Is X in R for all X? I'm asking this question as many ways as I know how, waiting for you to answer me. Yes. Do I have the same mother and father as myself? Yes. Right? Do they have, for every person, does that person have the same mother and father as that person? Yes. So this is a reflexive relationship. So this is reflexive. How about for this set A? A is 2, 3, and 4. The relation on this set A is that 2 goes to 2, 2 goes to 3, 2 goes to 4, 3 goes to 2, 3 goes to 3, and 3 goes to 4. We want to know if this is reflexive. So is X related to X, or is, gosh, that's supposed to be an R, or is X, gosh, my handwriting, I'm working on it, is X in R for all X in A? No, why not? Yeah, it's because there's no 4, 4. So 2, 2 is in there, that is good. 3, 3 is in there, that is good. 3 is related to itself, 2 is related to itself. However, 4, 4 is not in there, and it should be. Does that make sense? Okay. All right, number 3, we have A is the integers, so we're pulling from the set of integers here, and the relation on that set of integers is that x, y is in Z2, that's Z cross Z, when x times y is greater than or equal to 1. So is x in R for all x in Z? Or is x squared greater than or equal to 1 for all x in Z? Huh?
Oh, wait,
You have like 0.1 times a larger number and 0.1 times 0.1 isn't there.
These are integers, so 0.1 doesn't matter, but what does matter? 0 is a problem. Squaring a negative number, we're fine. It's going to be greater than or equal to 1. But squaring 0, still 0. And so that doesn't work. Does that make sense?
Yeah.
So 0 is an integer, but 0, 0 is not in R. So R is not reflexive. That's your counterexample, right? It says for all x in A, XX is in R. Every element should be able to look at itself under this reflection, if under this relation, if it is reflexive. Does that make sense or no? Yes?
is that, wait, is it because it's greater than or equal to 1? Is that what sets it?
Yeah, if this was greater than or equal to 0, we would be fine. But it's because it's 1, because 0 squared is equal to 0, which is not greater than or equal to 1. Okay. Number 4, A is the integers again, so we're x and y are integers here. R is the set of ordered pairs in Z cross Z where x is equivalent, that's what those, or congruent, you can use either one, those 3 bars, to y mod Z. So for reflexivity, we want to know, is x in R for all x in Z? Or is x equal congruent to x mod 7 for all x and Z? Yes. Yes, the answer is yes. But why? So this thing we can rewrite as x mod 7. Well, actually, let me back up and do this. Up here, this thing, and we'll prove this later. This is congruent to saying x, or equivalent to saying x mod 7 is equal to y mod 7, that they have the same remainder mod 7. Yes, right. 2 has the same remainder as 2 mod 7. Yeah? Yes?
I get that part.
0 has the same remainder as 0 mod 7.
The 3 lines means.
Yes. Means equivalent or congruent. But take the 3 lines out and use these 2 lines.
Okay.
For right now, we'll prove this later. We're gonna do like definitions of what it means mod, to be congruent mod, and D whatever. We'll do that probably Friday.
So when we see that notation, we can just like
You're not going to, I mean, you're going to see it for these three examples, but other than that, I will, yes, you can just change it, yes. And I will give you one more way to write it too. So is it true that x mod 7 is equal to y mod 7? I'm sorry, is it true that x mod 7 is equal to x mod 7 for all integers x? Yes. Yeah, x mod 7 equals, oops, x mod 7 equals x mod 7 for all x and z, so we're good to go. So this is reflexive. All right. Questions about reflexivity? Yes, no, maybe so. Emily, you're good? Do you want to think about that a moment longer? Yeah. Yeah. That is fair. Did I put more examples in here? Well, we'll do those. So the reflexive property says everything in your big set is related to itself under this relation. So, I mean, these two are really good examples that every integer, when you square it, is it greater than or equal to 1? No. Okay, so this relation that x times y is greater than or equal to 1 is not reflexive. It's not going to be true that every x maps to itself. But it is true here that every x would map to itself under this relation. And a bunch of things, you know, well, x is only going to map to things that are congruent mod 7, but lots of things will map there. Again, the mod thing we'll talk more about soon. So we'll move to symmetry, and I think after we get through doing these separately, when we do them all together, kind of, it's going to make them jive better, hopefully. And if not, we'll pause then. Okay. So we have here, we're looking at symmetry. What it means to be symmetric is, this is for A or X, Y in A. If X is related to Y, then Y has to be related to X. A relation has to go forward and backwards to be symmetric. So we have A, this set of all people. R is the relation consisting of pairs of people X, Y, where X and Y have the same mother and father. So we're going to let X and Y be people. We're going to assume the if part. So we're going to assume X is related to Y, that X and Y have the same parents. Is it true that Y is related to X? That Y and X have the same parents? Yes. Yes, so this is symmetric. Okay, this next one we have A is again 2, 3, 4. The relation R is 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4. So we're going to let A and B be in A. And we're going to assume AB is in R. Is BA in R for all of those? So 2, 2, forwards and backwards, fine. 2, 3 is in R. Is 3, 2 in R? Yes. 2, 4 is in R. Is 4, 2 in R? No. So this is not symmetric. Does that make sense to you? What's another reason why it would not be? Yeah. 4, 3 is not in there for symmetry. Good. Any other questions? Is that okay? All right. Now we're looking at integers again. Big A is the integers. The relation is the set of ordered pairs x, y, where x times y is greater than or equal to 1. So we're gonna let A and B, or x and y, be in Z, and assume x is related to y. That means x times y is greater than or equal to 1. Is it true that y times x is greater than or equal to 1? On this one, because we know that x times y is greater than or equal to 1, we get to assume that. So swapping the order of this multiplication won't matter. It won't change the outcome. So this is symmetric. Because for all x, y, where x is related to y, we get that y is related to x. Yeah, because 0 isn't going to be in one of the that makes this true. Right? We have to assume that this is true. If either x or y is 0, then this part wouldn't be true. So yeah. Yeah. So on this one, we need to have that first part be true. So that prevents the 0 problem, I guess, is the way to take that. All right, and then last, for symmetry, this is x mod 7 equals y mod 7. So we are going to let x, y be integers and assume x is related to y. That is that x mod 7 equals y mod 7. Is y related to x? Why? Yeah, y mod 7, the equal sign is an equivalence relation, so this and is symmetric, so this works. Y mod 7 is equal to x mod 7, so y is related to x. Yx would be in the relation R as well. Okay, good. Questions or comments so far? Transitivity. You're gonna have x, y, and z, I meant. X, Y, Z in A. If x is related to y and y is related to z, then x is related to z. The transitive property the same as it has always been. If A equals B and B equals C, then A equals C, right? So using this first example, A is a set of all people. R is the relation consisting of pairs of people x, y, where x and y have the same mother and father. So I'll use myself as an example. I am Emily, and I have the same mother and father as my sister, Diana.
And my sister Diana and my brother Drew also have the same mother and father. Do I have the same mother and father as my brother? Does that make sense? So my sister and me, we have the same mother and father. My brother and my sister have the same mother and father. Can we squish out either one of them, right, and say that that I have the same mother and father as the other one? All right, transitive property for the set one here. A is 2, 3, and 4. Transitive property says A related to B, B related to C, then A is related to C. So if we have here like A, B in this set and B, C in this set, then A, C is in the set, the relation. Do you see any problems?
I was gonna ask, can we use the same one twice?
Yeah, so like 2, 2, 2, 3, both in there, and so is 2, 2, so you're 2, 3, so you're fine. 2, 2, 2, 4. 2, 4 is in there, you're good to go. Any of them start with a 2 I have not mentioned? No. Okay. And then if I move to this one, I'm looking at 2, 3, any of them that start with 3. So 3, 2. Well, 2, 2 is in there, so we're good to go. 2, 3, 3, 3. 2, 3 is in there, so we're good to go. Yeah. 2, 3, 3, 4. 2, 4, which is in there, so we're fine. Are we okay so far? Janaya, are you okay so far? Okay. So we're looking for pairs that have the same ending and beginning numbers. Look up the same ending and beginning numbers and see if we can smash together, find an ordered pair that's got the ends. So we've got 2, 2, 2, 3. If we eliminate the middleman, there is 2, 3 in. Yep. 2, 3, 2, 4. We eliminate the middleman, is 2, 4 in. Yep. If we use 2, 3, and 3, 2, can we eliminate the middleman? Yes, 2, 2's in there. 2, 3, 3, 3. 2, 3 is in there. We're good to go. 2, 3, 3, 4. 2, 4 is in there, so we're fine. 2, 4 doesn't match up with anything. 3, 2 would go back with these two. 3, 2, 2, 2. Eliminate the middleman there. That works. That'd be 3, 2. It's fine. 3, 2. Gosh, I'm so tired of doing this. 2, 3. That is 3, 3. So we're fine. Yes, yes. I've left one off, right? 3, 2, 2, 4. That would give us, oh my goodness, these should not be equal signs. That would give us 3, 4, which is there, so we're fine. 3, 3 with 3, 2 is 3, 2. Yeah, I'm tired of doing it too. 3, 3 with 3, 4. is 3, 4. That's everything, right? Thank goodness. So this is transitive. Yes, sir.
3, 4. We don't do that.
There's nothing that starts with a 4, so we don't have a B,
Yeah.
because you need A, B in and B, C in. Right. But nothing starts with a 4, so we don't have anything to do with that.
It's ribbon, it's not
Hmm?
there. Can't be wrong if it's not there.
Right? Yes. The assumption part needs to be right. Okay. Questions or comments about any of that? Ready to do the next one? Okay. A is the integers. We're looking at the relation where it's the set of ordered pairs whose product is greater than or equal to 1. So for reflexivity, we are going to let x, y, and z be in z and assume x is related to y and y is related to z. That means what?
X is related to
That's what we're going to prove, Michael. So don't do it yet. What does this part mean? See, you didn't even hear. What does this mean about x being related to y? What does that give us? What does it mean for x to be related to y? Oh, I'm concerned now. Yeah, that x times y is greater than or equal to 1. And what does it mean that y is related to z? Yeah. We want to know, my gosh, we want to know, is x times z greater than or equal to 1? That would show us that x is related to z, right? Okay. The answer is yes, but why?
because if X and Y is greater than 1, just assume true, and Y times Z is assumed true greater than 1. And that means X and Z both have to be greater than 1.
It doesn't.
Or greater than
No. Why is it true? I mean, x could be negative 2, which isn't greater than or equal to 1. And this could still be true. What could y be that would make x times y greater than or equal to 1 if x is negative 2?
then it would have to be a negative number.
It would have to be a negative, right, to get something.
And then if Y is a negative, Z would have to be
Negative.
negative, and then a negative and negative positive.
Yes, Michael got it. So if any one of these is negative, then they're all negative. If any one of them is positive, then they're all positive. Yeah. And then that makes this a negative times a negative or a positive times positive, which is going to be bigger than 1 or equal to 1.
And when we assume it can't be 0, because it has to be greater than or equal to 1.
It can't need, none of them can be 0 because these things are true.
Gotcha.
So because x, y is greater than or equal to 1 and y, z is greater than or equal to 1, none of them are 0. Also, x and y have, is polarity a word for positive or negativeness? Okay, have the same polarity and y and Z have the same polarity. Thus, X and Z have the same, oh my gosh, polarity. So X times Z is greater than or equal to 1. Thus, X is related to Z and R is transitive. Hi, Eunice. We're on page 4. Only for a moment longer. How do we feel about that one? Good or bad? Good? Okay. We have the mod one again. Sorry, I'm gonna fix this. X mod 7, I'm gonna change this in my notes when I edit them again. X mod 7 is equal to Y mod 7. That's what makes these things be in the same, in this relation. So, what do we get to assume to show the transitive property here?
So, X related Y, Y is related Y.
Yeah, so we've got X, Y, and Z in big Z. We get to assume X is related to Y and Y is related to Z. So what does that mean?
X 17 equals Y 17, Y 17 equals Z 17, X 17 equals Z 17.
Nice work. Questions or comments? Janaya, tell me what's going on in your noggin. What's going on in your noggin?
The one that like actually makes sense.
Oh, good. Perfect. Okay, so I need 3 volunteers. Michael, Brian, Sherrod. Sherrod, you're in charge of the reflexive property. Brian, you're in charge of symmetry. Michael, you are in charge of transitivity, okay? So you're going to want to flip to those pages. No, not yet. Hold on. So a relation is called an equivalence relation if it is reflexive, symmetric, and transitive. So if for all x and a, x is related to x, that's reflexive. If it's symmetric, all x, y, and a, if x is related to y, then y is related to x, and transitive, the one we just did. If all of those things are happening, reflexive, symmetric, and transitive, then the relation is called an equivalence relation. And we can use this little squiggly notation for the, instead of an R. Once we know it's an equivalence relation, we can do the little squiggle. Cool? Cool. Okay, so Sherrod, you're doing reflexivity. Brian, symmetry. Michael, transitivity. Reflexive, symmetric, transitive. Oh golly, my colon's got way out of control there. These are the same 4 relations we've been looking at to decide if they were reflexive, symmetric, or transitive. And so now, since we're not all going to flip back, we're going to trust our classmates to do that for us, to tell us if these things are reflexive, symmetric, and transitive, and then we will know if it is an equivalence relation or not. Sherrod, can you go for me? What about the reflexive property on number 1? Go back to page, I don't know, 2, page 2. Number 1, is it reflexive?
Yes.
Number 2, is it reflexive?
No.
Number 3, is it reflexive?
No.
How about number 4?
Yes.
Great. Brian, number 1, you're on page 3. Number 1, is it symmetric?
Yes.
Is number 2 symmetric? Is number 3 symmetric?
Yes.
Is number 4 symmetric?
Yes.
Great. Michael,
Yeah.
you're on page 4 maybe.
Yes.
Is number 1 transitive?
Yes.
Is number 2 transitive?
Yes.
Is number 3 transitive?
Yes.
Is number 4 transitive?
Yes.
Ooh. Okay. Emily, you're in charge now. Is number 1 an equivalence relation? Is number 2 an equivalence relation? Is number 3 an equivalence relation? Is number 4 an equivalence relation?
Would we write it as like the X squiggle Y or A in the specific equations?
I wouldn't at all. It would just be in, like, if you knew something was an equivalence relation and you were using that to prove something else, you could say like, because A is equivalent to B or whatever. But I wouldn't use, I would just use the R for element wise, use R. Okay. So that is equivalence relations and how they are defined. And then we're going to do some stuff with proving that things are equivalence relations. Are you so ready? Okay, so you'll notice the first one we're going to prove, number 1, I will read that definition to you in a minute. That first one, number 1, is the same relation we were looking at on number 3. It is number 3, the relation that we have practiced a couple different times. For us, we have problems when things were equal to 0. And so if we take the 0 out, does that make it okay? If you look at it up here, the problem was the reflexivity property. And that was a problem because of 0. So if we remove 0 from the situation, does it become an equivalence relation? And the answer is yes. So we're going to prove that in a minute. But what we want to do first is talk about equivalence classes. So an equivalence relation on a set, you have some equivalence relation R on a set A. The elements that are related to an element, that's its equivalence class. So if you think about, like, the example I would use is like me, right? So when you're talking about an equivalence class of an element, you use the little square brackets, okay? So my equivalence class under that relation of parents, yes, mothers and fathers, right? My equivalence class is a set of all people where those person is related to me under this relation. So for me, this equivalence class is my brother. That's not him, that's my sister's name. It's fine. This equivalence class is my brother and my sister, and me, because I have the same parents as myself. Right, so it's the set of all elements that are related to that particular element. Does that make sense? It's the collection of things that, like, if it's equivalence, right? Think about mod stuff. This is a great example. Equivalence under mod 7, right? There are the things that are equivalent under mod 7 are like 1 and 8 and 15 and 22, right? So the equivalence class would be broken up into those things. How else should I say that? Let's do this officially with maybe not my example here, but like, so the equivalence class of A is going to be the set of all things let's go with X in big A, where X is related to A. Or A is related to X, the order doesn't matter there because this is an equivalence relation already. So it's reflexive, so the order doesn't matter. I mean, it's symmetric, so the order doesn't matter. So, and it's reflexive, so I have to be in my own equivalence class. Right, so I'm in my own equivalence class and the order doesn't matter if they're related to me or I'm related to them. Right, so X related to A or A related to X, either one works, and it'll be the same.
So if you were to put like a 3 in there, for instance, it'd be like A's. Like just as an example, like the A1 that we did was X, and then you would kind of be equal to A, B, C. for instance.
Yeah, right, like if this was, let's do it for this example, okay? So we have these two, this equivalence relation, sorry, we're gonna prove it's an equivalence relation, we don't know that yet. But it is one. So, that A is related to B if and only if A times B is greater than or equal to 0. So like, the equivalence class of some element is gonna be all of the things that are related to that element. So let's pick something in here, anything in here, somebody. Okay, so the equivalence class of 1 is going to be the set of all elements, so X and Z, toss 0. Do you all remember this set notation? This is the set subtraction. It's a toss. Yeah, sorry. This is Z without 0. Okay, so X is an integer that is not 0. And this would be where 1 is related to X. Or here, that X times 1 is greater than or equal to 0. So what do those things look like? So the equivalence class of 1 is a set of all integers where 1 times that integer is non-negative. What would those things look like? Would 7 be an equivalence class of 1? Is 7 times 1 greater than or equal to 0? Okay. Would 17 be in the equivalence class of 1? Is 17 times 1 greater than or equal to 0?
Yes.
Would negative 2 be in the equivalence class of 1? Is 2 times negative 1 greater than or equal to 0? No. So what do the things in this equivalence class look like? And can't be equal to 0, so just positive integers. This is Z plus. Yeah. The equivalence class of, what would the equivalence class of 2 look like? Do y'all buy that? Brian's right. Would it be the same? Yes? Because 2 is in here, right? And once it's in an equivalence class, that's its own equivalence class too. Yeah? Okay, so give me something that's not in here that is in here. And we'll come up with another equivalence class. Okay, so if we use negative 1, this would be the set of all X in Z toss 0, where negative 1 times X is greater than or equal to 0.
All the negative integers.
Yep, that's Z negative.
This might be getting mad. I assume like if we were to keep like putting it as an integer in there instead of like 1, negative 1, blah, 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 that it would change relatively. Like the integer would change relatively to fit what we're putting in.
So yeah, the whatever we put here, yes, would change. So because I'm replacing this in this relation with the thing we picked to do the equivalence class. And you're identifying what the other thing has to be to make the thing true still. So these are the only two equivalence classes of this relation. It is either the positives or the negatives that are related to one another. Yeah.
Where does 0 fit in?
It doesn't because it's been tossed.
Oh,
Yeah. And that was the important thing, because if 0 is in there, then this thing is not reflexive. And so we don't, we're done. Oh, well, I guess 0 could be in there now.
So that would have to.
Because we had 1. I'm going to change this too. I'm going to change this to be a positive 1. We don't need to get rid of 0. If we are greater than or equal to 0, but we do need to get rid of it if we're greater than or equal to 1, which is what we were doing before. So I'm going to fix that. We're going to make this a 1. These are 1s, and that's still fine. Those are all still fine because we've tossed 0. Those things are not untrue with 0 tossed, though. We're fine. Yes. We just don't need to toss 0 if we're greater than, if we could be equal to 0.
wait, so if you were, like, 0 was included, how would that?
0, and this is a great question, because if 0 is included, it would go in both of those equivalence classes, and that's bad news bears. If 0 was included, then it would be allowed to be in either one of those equivalence classes, yeah? And you're not supposed to be able to be in 2 equivalence classes. So that would have to break something else. Transitivity. It breaks transitivity. That's why we need it. Because if we could be equal to 0, if you did, like Brian just said, if you did -1, 0, 0, 1, these are both -1 times 0 is an R, and 0 times 1 is an R, right? This is your A and your B and your B and your C. But -1 times 1 would not be greater than or equal to 0. So -1 is not related to 1, so it's not transitive if you don't toss 0. That would be why. Good work, everyone. Let's do it with this anyway. We're fine. Yeah? Okay. But now we understand why I needed to toss 0. And now I understand why we needed to toss 0. So everybody's on board. Good. We're like, something's broken because this shouldn't work. Good. This is how you do math. You make it make sense. We just made it make sense. Okay. So we are going to prove that this is an equivalence relation. We have identified 2 distinct equivalence classes, so we are good to go. So, scratch work. So I'm going to leave myself some space to do scratch work. We have a whole page to write this proof on. Okay, so to prove something is an equivalence relation, we need to show 3 things. We want to show that it is R is reflexive. We want to show that R is symmetric. And we want to show that R is transitive. Okay, so what does it mean for R to be reflexive? Yeah, for all A, B, and Z toss 0 is
oh, sorry, for all A and B tossed 0, is A squared greater than or equal to 1?
Yes. Yes. I'm glad I did that scratch work. Just kidding. I am. I'm glad. I don't know how to do any more there. Like that's it. Yes. Uh, a non-negative thing squared is still a non-zero thing squared is non-negative. Yes. Okay. Symmetry. We have we want to let A, B, and Z toss 0. We want to assume A is related to B. We are going to show B is related to A. What does it mean that A is related to B? That means that A times B is greater than or equal to 1. Does it follow that B times A would be greater than or equal to 1? Yes, because multiplication is commutative. All right. Last but not least, we are going to let A and B and C, B and Z toss 0. You're going to assume A is related to B and B is related to C. We will show that A is related to C. If A is related to B and B is related to C, what do we know? No, we don't know that yet. Yeah. Yeah, we know that A times B is greater than or equal to 1 and B times C is greater than or equal to 1. So A, B, both positive or both negative. B, C, both positive or both negative. So A and C are both positive or both negative. So A times C is greater than or equal to 1. And then that means that A is related to C. Okay, we probably have time to write this proof if you're ready. We certainly have time to write this proof if you're ready. Okay. So I'm going to rewrite that sentence. So for A, B, and Z, toss 0. Define a relation R by A is related to B. Hold on. Sorry. For A, B, and Z toss 0, let R be a relation where, my gosh. A is related to B if and only if A times B is greater than or equal to 1. We will show R is an equivalence relation.
First, let A be an element in Z, toss 0. Clearly, A squared is greater than or equal to 1. So R is, no. So A is related to A and R is reflexive. Now, let A and B be in Z toss 0 and assume A is related to B. That is, A times B is greater than or equal to 1. Clearly, B times A is also greater than or equal to 1. So B is related to A and R is symmetric. Finally, let A and B and C be in Z toss 0. Assume A is related to B and B is related to C. Then A times B is greater than or equal to 1 and B times C is greater than or equal to 1. We know A and B are both positive or both negative. Similarly, B and C are both positive or both negative. Thus, A and B have the same sign. Can I say that? Have the same sign. This means A times C is going to be greater than or equal to 1, and A is related to C. Thus, R is transitive. Since R is reflexive, symmetric, and transitive, it is an equivalence relation. God, my hand hurts too, but I think we're done. Do you have any questions or comments? Okie dokie, I will see you on Friday. I will have at least one homework assignment to give to you on Friday to complete. Okay. Don't wait until then to like look at this again. Probably a bad thing to do.
I'll probably post homework online so you can look at it before then. Cool? Cool. Goodbye. I will extend whatever homework was due last week to be due at the end of this week, if you have not done it yet. The online homework. I will also have your test for you on Friday. Look at me go. I'm gonna kill it this week. Yeah. You just missed all of me not killing it earlier, so it's fine. Eunice, can you tutor this afternoon? Okay. There's only one student so far.